Welcome everyone to our data science and computational statistics seminar of this semester. So it's my great pleasure to introduce our speaker today, Dr. Truong Vĩnh Lan. Lan obtained his PhD in 2018 from the National University of Singapore. He did a short postdoc there for 1 year, and since 2020 he moved to Cambridge, where he currently is a research fellow. It's a great pleasure to have you here. And Lan research interests include information theory, machine learning, communication, and statistics. So today he will talk about the replica analysis of the linear models with Markov or hidden Markov signal. So we will record the talk, and if you have any question, you can simply directly ask the speaker, or you can type the question into the chat box. Okay, so thank you, and welcome, Lan, please.
Thank you, Jung, for your nice introductions. It's a great honor to have a talk at your seminar series at the University of Birmingham. Today I will introduce one of my research work, replica analysis of the linear model with Markov or hidden Markov signal priors. So here is the outline of my presentation today. In the first part, I will give motivation for this work. In the second part, I will provide our problem setups and some of our main results are given in the third part of the talk. And I will conclude my talk by providing some numerical results to illustrate our results. So the linear models can be represented by the following relation. Y equal to phi x plus w, where y is a vector in m-dimensional space representing the observation, and x in an input vector in n-dimensional that vector we would like to estimate, and phi is a metric which can be a random metric with dimension m by n, and w is a noise vector in m-dimensional. So this model appears in many applications. For example, in code division multiple access and multiple input, multiple output in communications, in compressed sensing, in signal processing, and in linear regression and feature selection in machine learning. So the main question of this problem is to estimate the vector x. We assume that x equal to x1, x2 up to xn. So this is an n-dimensional vector from a vector y representing m observation, y1, y2 up to ym. So usually in research literature, researchers assume that the vector x has IID component. This means that identically independent disputed element. However, this assumption looks not practical in many applications. For example, in communication, in MIMO system in communication, this means that we have multiple antenna. We use multiple antenna at the base station, and we use multiple antenna at our devices. For example, in cell phone, then the gap between the antenna in cell phone is very small. So the assumption that the signal transmit from all antenna independent look not practical. Usually two antenna, two symbol in two neighboring antenna usually they interfere with each other. So that is one example that why IID assumption look not practical. Or in machine learning, for example, test service, one symbol usually depend on previous symbol. In natural language processing, text to speech or speech to text, it also belongs to the case that the vector x is not non-IID. So because of this, in this work we consider the K, the vector X, it's not IID. More especially, we consider two models. The first model is when the vector X is generated by a Markov model on some Polish space H. We limit the Polish space in real number. And the second model is when X is generated by a hidden Markov model on some Polish space also in real number. So in the first figure, so we assume that X1, X2, Xn form a Markov chain. And in the second model, we assume that the Xn, X2, Xn generated by a Markov chain, gamma 1, gamma 2, gamma n. So two model is different, right? The first one is X1, X2, Xn a Markov chain, and the second one we call hidden Markov chain because the sequence S1, X2, Xn maybe not a Markov chain, but it's generated by a Markov chain, and this Markov chain usually hidden. So this model appears in many applications like machine translation, speech synthesis, or handwriting recognition in machine learning and signal processing. We also made other assumptions. For example, the number of measurements scale linearly with signal dimension, so n equal to m beta for some beta greater than 0. So this assumption appear in many, in almost all the research paper in these areas. I don't know the original reason, but one reason for communication is that a linear model can represent a coding scheme in communication. And the coding scheme usually have the fit rate and the rate related to equal to beta or 1 over beta. That's why usually we assume that n equal m beta. And we assume that measurement metric phi equal to a square root at, where at is a diagonal metric with element S1, S2 up to Sn. And we assume that all element S1, S2, Sn have the same distribution, assume that some zero distribution P at. And we assume that vector A had all element is IID, and each element had 0 mean and variant 1. So we normalize over square root m, that this one. So some variant of each rows has equal to 1. And we assume the noise vector W is standard normal distribution, so in m-dimensional space. So our target is to estimate the average minimum mean square error. Here is the average minimum mean square errors and average mutual information. So we assume here EX given Y5, here is MMSE estimator, and this is the mean square error of the estimation. And we would like to estimate the average mean square error of our estimation, where if this is the MMSE estimator. And we also would like to estimate the mutual information. The mutual information and free energy of the model related to only a plus or minus some constant. So estimate mutual information, estimate free energy, it looks like the same. To optimate this quantity, usually we use a replica method in statistical physics. In Tanaka in 2002 and Guo and Verdu in 2005 use replica method to study multi-user estimator. So study linear model, we can understand the multi-user channel look like a linear model that we can consider before. And they show that under a generic posterior mean estimator, for example, MMSE, special K, the multi-user channel is decoupled. Essentially, is that they can convert the estimation problem in n-dimensional to an estimation problem in only one-dimensional. That is the idea of this results. And in our work, we also prove that for the Markov chain, the decomposition also happen. But the problem is what channel the decomposition will be turned into. that is the question in this work. And Barbier and Margaret in 2017 show that replica prediction for the linear model with IID prior exact. This means that they use a mathematical recurrent analysis to show that the replica prediction for the linear model with IID model is correct. So this means that we can use replica prediction for the linear model. However, they proof only apply for the IID prior. And in this work, we work with the case that the signal is correlated. So the reason why replica method is not really recurrent, if we view from a mathematical viewpoint, is that we in replica methods we use some assumption, and these assumptions look very hard to verify by using standard mathematical analysis. For example, we assume that if we would like to estimate limit of this quantity, we estimate this for some positive integer number v nu, and then we take the limit that we obtain when nu obtain tend to 0 to obtain the limit of the quantity when nu tend to 0. This assumption look not really not accurate. However, it correct in many cases, and it's acceptable in many research literature in statistical physics and communication and other fields. And they assume that the order limit order of n tend to infinity and nu tend to 0 can be interchanged. So in mathematics, we can see many theorems to show that the interchange of limit can be workable. For example, Mosswood's theorem so that when one limit in is conversion uniformly and other limit is conversion pointwise, and we can interchange, for example. So this replica actually we can this assumption is an assumption in replica methods, but we can prove it recurrently by using mathematical analysis. And the third assumption is that usually when we use a replica method, we estimate this quantity, this is posterior distribution. We use a log deviation theorem, and we obtain some results, which is an optimization problem. And optimization problem of this optimization problem is obtained by we use the replica trick. It means that we use many copy of a random variable. So in replica method, they assume that the optimizer of this optimization problem is symmetric with respect to the permutation of new replica indices. This means that they assume that the optimizer has some structure. Optimizer have some structure, some nice property, some symmetric property. So that is three main assumptions in replica method, and it look hard to prove that they are correct from mathematical viewpoint, but in practice, in many applications, we can see that it works. For example, in linear model with IID component. So because we put some assumption that we cannot verify, so we need to use something to verify our results. So in this work, we use two methods to verify our results. The first is we use MCMC method. So MCMC methods is a class of algorithm to sample probability distribution. in which corresponding to sample function. We can understand the sample function. The way that we sample the function is that we can construct a Markov chain such that this Markov chain has stationary distribution coincide with probability distribution that we would like to sample. And then we touch sample of this Markov chain. So there are a lot of algorithm to construct a Markov chain which has a stationary distribution is the probability distribution that we would like to sample. For example, Metropolis-Hastings algorithm is one of the algorithm. And it works with you this algorithm to verify the correctness of our replica prediction for linear model with Markov priors. However, this matters not always feasible in programming because of complexity. So we need to use some other methods. Also need to use other methods. So for linear model with hidden Markov, because the high complexity, we cannot use MCMC. It's difficult to use MCMC. So we use another method called approximate message passing algorithm. So approximate message passing algorithm it usually used for spark signal recovery and compressed sensing by Dohono, Margalecki, and Montanari in 2009. And this algorithm achieved state-of-the-art performance of many high-dimensional statistical estimation problems. And its complexity is very low. And in this work, we use an AMP algorithm called turbo AMP to verify the correctness of the linear model with hidden Markov prior. So in summary, to verify the correctness of replica prediction for linear model with Markov chain, we use MCMC. To verify the correctness of the linear model with hidden Markov prior, we use AMP algorithm. So because the linear model with hidden Markov prior different from the linear model with IID priors, so we need to develop some new techniques. For example, the optimization problem now is an optimization problem. When we use the log deviation theorem, we obtain a function of Perron-Frobenius eigenvalue of a non-negative metric. This is the log eigenvalue of a non-negative metric. Non-negative metric here is the all element greater than equal 0. And different from non-negative definite metric. It's different. And then we optimize this a function of Perron-Frobenius eigenvalue. And so we need to take some kind of derivative of this eigenvalue with respect to a metric. And then we all use some mathematical analysis, optimization. For example, we show that the asymptotic optimal solution is a convex combination of several moment generating functions, and all these moment generating function we can estimate more easier. So now I present some of our main results in this work. The first result is for the linear model with Markov prior. So we assume that Xn form a Markov chain, and our main result is so that the linear model decoupled into n estimation channel with input xi and state xi-1 at each time I from 1 to n. So this means that we show that we can change the optimization problem, the estimation problem in n-dimensional, because we would like to estimate the signal x in n-dimensional. We show that we can change the estimation problem in n-dimensional to an estimation problem in only one-dimensional space. And here is just the channel that we did a single one-dimensional channel that we convert to. We convert the high-dimensional estimation problem from high-dimensional to this channel. So after we prove that, we only need to estimate. So the free energy of the linear model with n-dimensional becomes the linear, the free energy of this channel. And the MMSE of the n-dimensional problem becomes the MMSE of this single channel, and then we can estimate more especially we here it the free energy of the channel. So when we fit x naught equal x naught here, we can estimate the free energy of the channel. And when we take linear combination of this conditional free energies, when we set x naught equal to x naught, we obtain a quantity we call G. And we show that the free energy of the linear model, original linear model, exactly equal to G. And every MMSE also, we obtain exact formula for this. That is MMSE for the channel. And we can represent a linear combination of some conditional MMSE. And the second, for the second model, that linear model with hidden Markov prior, then we show that the channel, the estimation problem in high dimensional can be converted to estimation problem in one dimensional. Here is the channel. However, state now is x minus 1 and gamma I minus 1. So this means that we have n channel, and each channel we have two states. Instead of one state, really different from the linear model with Markov prior, we only had one state. Now we have two states. The reason is because for the hidden Markov prior, we can see that xn, gamma n, we form a Markov chain. So that's why we we can make use of the results for the linear model with Markov chain to obtain the curve results. So here is the formula for free energy, and so it's a linear combination of some conditional free energy, and also the formula for the average MMSE when the dimension n very large. So in the last the talks, I will present some numerical results to show that the replica prediction are correct for many cases. So the first example is we consider the assumption a linear model with Markov chain where the sequence S1, X2, Sn is a Markov chain with alphabet x equal to minus 1, 1. And the stochastic matrix is 1 minus alpha, alpha, delta, 1 minus delta for alpha and delta in 0, 1. And we choose alpha and delta in simulation. So we compare the free energy achieved by replica prediction and MCMC for linear model with binary value. Markov prior actually is minus 1, 1 value Markov prior. The reason why we only need to compare free energy of our replica prediction and simulation, but we don't need to compare the MMSE because we know that the MMSE and the free energy has a relationship. So like MMSE equal to derivative of the free energy with respect to the signal to noise ratio model. This means that if we obtain one, we can obtain another. So to construct a Markov chain in the MCMC method, we need to define what is the state and what is the transfer function, transition property function. So here is how we define the state. So it's the vectorization of a matrix, phi t. YT, sorry, it's an error here, so it should be phi t and YT. And the transfer function is we define g xt plot 1 given xt is normal diffusion with state xt with mean st and covariant mn plus n, imn plus n. And here the plot, the first plot is for the case alpha equal to delta equal to 0.5. This means the Markov linear model with Markov prior will become the linear model with IID prior. So IID prior can be considered a special case of linear model with Markov prior. And when we put alpha equal to delta by equal to 0.5, we can see that the curve between free energy that we obtain from the replica method and free energy by simulation is nearly coincide to each other. And for the symmetric case where alpha equal to delta equal 0.3, two curves also very close to each other. And even in symmetric case, two curves is nearly coincide to each other. And now we give an example to verify the correctness of our replica prediction for linear model with hidden Markov priors. So we assume that the sequence x1, x2, xn is generated by Markov chain gamma 1, gamma 2, gamma n, where property of Sn given gamma n defined by Vn, and here is the Gaussian distribution, and here is equal to 0. It means that the x, the random value Sn will take the Gaussian distribution with property Vn and take the zero value with property 1 minus Vn. And here is the stochastic metric of the Markov chain gamma n, 1 minus kappa gamma, gamma kappa, and this one for gamma and kappa we can choose. So as I mentioned before, we assume that the random variable xn can take the value 0 with property 1 minus Vn. So this means that the sequence xn is sparse. And to verify the correctness, we use a version of AMP called Turbo AMP. This algorithm is well developed by Schlitter beyond the idea of belief propagation in Bayesian inference and communications and turbo code in coding theory. So the main idea of the algorithm is interchange iterates between exploitation of observation structure, so sparsity of the sequence Sn, and observation structure and sparsity pattern of this Xn. And the reason why it's called Turbo AMP because it resembles turbo code in coding theory. And after we obtain a massive parsing algorithm, we draw an approximate version of the massive parsing algorithm here by using approximate massive parsing framework by Dohono, Maleki, and Montanari in 2009. So that is the essential idea of the Turbo AMP by Schlitter. So here is algorithm. So we consider a subplot. For example, when we put kappa equal 0.5, gamma equal to 1, that means the xn is an IID sequence. We see a two curve is nearly coincide. And one for asymmetric case where kappa equal 0.3 and gamma equal to 0.8, we see the gap between two curves also is very close. So in summary, in this talk, I mentioned about the linear model with Markov and hidden Markov priors. And we consider the activation problem, and we show that the activation problem in n-dimensional can be converted to activation problem in only one-dimensional. However, the channel here is the channel with state. It means that we assume that there are state available at encoder and decoder. So if you work with information theory, you will be very familiar with channel with state. And the state distribution follows the stationary distribution of the corresponding Markov chains. And we also provide free energy and MSE formulas when M and N tend to infinity by using replica method. And we verify our replica prediction by MCMC for linear model with Markov priors, and AMP for linear model with hidden Markov priors, and the gap very small. So that's all for my presentation. Thank you. If you have a question, please let me know.
Okay, so thank you, Lan, for the very interesting talk. And are there any questions from the audience, please?
Can I ask a very quick one? Thank you very much for the talk, by the way. If you go to last two plots, is it correct to kind of assume that the method works much better in the symmetric case than the asymmetric case? Because although they're both very close, but it's kind of obvious that in the asymmetric case, there's a little gap over there.
Does
this always be the case, or it's very much depends on the examples?
Usually, because usually in theoretical, because we take N and M tend to infinity, and when simulation we set M and N is finite, right? So limit the replica results we obtain is when we assume that M and N tend to infinity, and when in simulation we assume that M and N is quite small. And we take N and M finite. Usually we cannot take M and N too big, because when too big is complexity very high. So we take like M equal 50 and N equal 100, and we have magic M by N, right? So that is why we have still a small gap. But I think that when we change M and N big enough, then the gap will be small.
So if we have both large M and N, even they are not the same, you would expect the gap will be much smaller.
The gap will be small.
Okay. Thank you very much.
Thank you. Are there any questions, please?
I would have a question.
Yes, please.
Thank you again for your interesting talk. So this is really new that you introduce different prior with dependency. So I think, but it's possible you're able to solve it because you still keep the IID assumption in the design matrix, or could one sort of put in more dependencies in the design matrix and have still possibilities of solving the replica problem?
If we put assumption on more on the metric, then the problem, I think that it will be hard. It will be harder. Yes, it will be harder. So we can imagine that for the IID, Xn is IID, then we can change the function of x1, x2, xn into a function of f1, x1, f2, x2, fn, fn. Then we can, when we take logarithm and we take limits 1 over n, we obtain the one-dimensional, right?
Mm-hmm.
So we can imagine that. So for the Markov prior, there's difficulty when px1, x2, sn equal to px1, px2 given x1, and px2 3 given x2, pxn given sn minus 1. So there is a dependency here. So the purpose of this talk is how to remove the redundancy here. That is make the problem is harder than the IID case.
But I think simple extensions like rotationally invariant design matrices, that's possibly something you can do. I have a second question on kind of rigorous analysis. So nowadays people often are able to solve the dynamics of the AMP algorithm in the large N limit and sort of show that AMP converges to sort of on average to the replica result. Would that also be something that is doable in this problem?
Yes,
I mean, the Montanari's work and Schnitter and other people.
Yes, I mentioned that there's some work now. They show that the replica prediction is for it's exact, so we can use rigorous mathematics analysis for the linear model. But however, they assume that the vector x1, x2, xn is IID.
Yes.
Usually IID, yeah. Because there are some analysis we require that x1, x2, and IID.
Okay. So even in the dynamical approach.
Usually they assume IID. Yeah.
Okay, that's interesting. Okay, thank you very much.
Thank you for interacting question.
So I have very related question. So you mentioned that in the IID case they can verify the replica trick, and it might be hard in the general settings that you assume in this. But for instance, for the particular example, the 2x2 Markov chain, is there any chance to prove it for that particular example?
For two, the main difficulty here is we show that the estimation problem in high dimensional can be converted to one dimensional. This means that when we assume that the signal dimension is very large, n tend to infinity and m tend to infinity. So if we consider a fit metric with the a metric with fit dimension, then then the question is whether we can change the estimation problem to an estimation problem in one-dimensional problem or not. It's not. I think it's unsolvable. Unsolved now. Usually we have to assume that n very large and m tend to infinity, then we can convert. But when n and m is finite, then problem is maybe hard. Yeah. But I think that maybe use some like concentration inequality in mathematics. Maybe we can obtain some similar results. I haven't checked in that direction.
Okay, so maybe very naive question from the very beginning related to the question period. So I don't understand why the random list in the matrix 5, the design matrix, right, in the language, why you assume both 5 and W are random? Can you simply consider only W as random? I mean, where the noise, where the different noise comes from?
Yeah, actually, this is maybe originates from communication. So in communication 5 here, communication channel. So X is the signal that we would like to transmit over a channel, and phi here is channel.
Okay.
So the effect of channel, and in the receiver, for example, in the cell phone, usually we have a receiver. Then they call some noise. That's why we need to apply a noise here.
Okay. Noise, so basically, you can assume that they have nothing to do with each other.
Yeah, I think this is just
I see.
from communication viewpoint, maybe. Yeah.
I see. Interesting. Thanks.
Sorry, could I ask another question? So very often when your x's are kind of constrained to be binary variables or something like that, there's often that you have phase transitions in coming out of the replica result, and they're also reflected in the dynamics. So is there something you do see here in your analysis? Oh, wait a minute. Yes. Yeah. You know what I'm referring to? Possibly if there is a mismatch between the true the data generating mechanism and the prior assumptions. So there are all these kind of phase transitions, I remember. Do you see them in your analysis?
Yeah. Actually, in this work, we assume that we have a mismatch we can has mismatch between the distribution of X and the distribution of that we consider receivers.
Yes, yes.
And the result is also the same. Yeah.
Oh, so you see these
we can see
phase transitions. But often I think in phase transitions it may be that the replica symmetric result is there's some replica symmetry breaking and all these kind of things. Is there something there's this kind of Almeida-Thouless line and all these kind of things that sort of, from a physicist's point of view, tell you when the replica symmetry is not working? That should be also possibly somehow contained in the analysis.
It's actually yes. Actually, we just verify our results for some example. We cannot verify for every very example. So sometimes the replica assumption it work with some example. We need to like replica breaking assumption, because we assume we put assumption here. Structure of the solution, for example, structure of Q star here. We assume that they have substructure, but for the general problem, it may have not decoupled structure. But I think that for this problem, when the matrix is IID and the vector X has Markov or hidden Markov structure, this assumption it look good enough. For general, it may not work, but for this example, I think that it works. But I cannot prove it rigorously now. So
I understand. Yeah. Thank you. Thank you very much.
Thank you. Yeah.